Hey everyone, my name is Daniel and I am the TA for section AB. And as I talked about in our quiz section, I'm here to just walk through questions 1 through 4 of homework 1. And in our quiz section, as you can recall, we did go through how to set up each question for questions 5 through 8. So if you still do have any questions on 5 through 8, please come to my office hours. It's going to be on Tuesday, 5 to 6 p.m. via Zoom. It's a great opportunity to answer any last minute questions you have on the homework that will be due on every Wednesday in the morning. So please take advantage of that. I'm here to help. So let's just start with question 1. It's asking you to find the pressure gradient at a specific point, A, B, and you're given the pressure field expression as shown in the question right here, and you're given the constants. So it's very helpful. So let's first remind ourselves of the definition of a gradient. And quite simply, a gradient just takes the partial derivatives of a function. So let's just remind ourselves of the actual expression. So gradient is given by the del operator right over here. It's an upside down triangle. Some people also put a line right here. Then it's given by, we have lowercase delta to denote a partial derivative. So we have a partial derivative of whatever function. This is the generic expression, this the specific function. And then we have the unit vector. This is also like the I unit vector, same thing. Oh my gosh, it's a big eraser. Great. Then we have, as you can guess, we have the same partial derivative with respect to y, the unit vector, and then we have z. So as you can see, the definition of a gradient just takes the partial derivatives of the function. So it's pretty simple. And then when we relate it to the actual pressure gradient, we're going to put this right over here. And we need to remember that the gradient is still also a function with respect to x and y. So let's remember that. It's very helpful because we have a point right here that looks like we can use to plug in to answer the question. So that means we're going to have the partial derivative of p with respect to x. But we still have our x unit vector. Then we're going to just keep going with respect to y. Then luckily we have no z in this question, so it's a little more simple. So as we can see, looks like we have 2 partial derivatives that we do need to find. Great, so what you're going to do after this step would be to figure this out. And that would be your next step. So actually, let's just work through one of these partial derivatives together. Please make sure that your partial derivative knowledge is refreshed and ready to go. I usually won't work out these problems this much, but since it's just the first one, don't mind going over it. So we have rho, and then it's important to denote rho differently than p. It's really important. It can mess you up. You will lose points. So just make sure that you can really denote that as a rho. And then we have b squared. So these are constants, so they stay when we take the partial derivative. So now we're just dealing with everything with respect to x. So first we have sine x over a. So that becomes, as we know, cosine x over a. Then we have chain rule times whatever the derivative of inside the expression. So that is 1 over a. Then we have sine y over b, and there's no x term, so that's a constant, so we just keep that in there. And then we have plus 2x over a. So taking the partial derivative with respect to x is just simply 2 over a. So right away, easily, we already got the first expression. So you just need to do that in respect to y now, and then you just plug it back into this function right over here. And I'm denoting this with the blue arrow. And great, you have your generic function. And then now you're going to actually at point A, B. And right away, we can see that if you do plug in A and B, let's just say in this first half of this equation with the partial derivative with respect to x, you can see that some terms do cancel out. So for example, this cosine is like A over A, so that's just cosine 1. And then we have 1 over A times sine B over B, which is just 1. So it looks like we have some more simplification that could happen. So just keep in mind for this, you do also need to know your trigonometry. So please make sure that that's still up to date. You can see cosine 1, sine 1. If you can recall, the double angle identity for sine. And I'm just going to also just put it here for now. Usually won't give too many hints like this, but hopefully this is helpful. Great. So as you can see right away, it's going to give a pretty easy way to simplify this expression even further. We will be looking for that, so just keep that in mind. And then you should essentially have, in the end, an expression P, and you will give us an expression at the point A, B specifically, not the generic one over here that you find with the blue arrow. But down here, after you plug in point A, B, and simplify as best as you can. So that is question 1. Great, now moving on to question 2. So we are given an expression for the pressure field, so similar to question 1. Then we have X, Y, and Z as space coordinates and T as time, and we're given some constants, but it's important to highlight the important parts. We are tasked to find the pressure gradient from the pressure field. That's all. So we're not given a specific point as the previous question. So it's really important to first see what the question is identifying, know what definitions we do know, and work from there. So similarly to the first question, let's just remind ourselves of the gradient. We can skip the generic definition and go straight into the pressure gradient as we were talking about in the previous question. So we know that is denoted by the del operator, P, and then we can see we have X, Y, Z. So you can choose to keep this in. It's just helpful to remind yourself that it is a function. So right away, we know we have lowercase delta to denote the partial derivative. Then we take the first one with respect to X, and then we have that unit vector. The same thing, partial derivative with respect to Y. Then we have the partial derivative with respect to Z. And this is just a definition that you want to know by heart. We'll be using this a lot. So just keep this in mind. You're basically taking the partial derivative. I know this notation can be confusing, but in the end, you're just taking the partial derivative of a function. Or you just could be taking the derivative of a function, right? So it's really similar. So don't be too afraid of this notation. So that means we need to find, like last time, 3 partial derivatives, put them back into this equation, and you're done. So just to work through it, let's do one more together. We need to find all of these. So let's just work through the first one, pressure at 0. We're just going to eliminate it when you take the derivative, as you all know. So let's keep going. Then we have 1/2 rho. Again, please note that very well. Then we have v squared. Then we have this bracket, the same thing as parentheses, which helps it denote it a little easier. Then we have 2xyz over L cubed. So simply, that's just 2yz over L cubed. How easy is that? Right. Then let's just check the second one. So right over here, let's just be really careful with the squares. Right away, you can just first distribute the squares out. So that would be 3x squared over L squared. Then it's pretty simple after that. It's just simply 6x over L squared. And then that third component doesn't have an x, so it's treated as constant. So it is eliminated. So that is your first partial derivative. And just do that for with respect to y and with respect to z. Then you plug it right back into this function right over here denoted by the blue arrow. And that's all we need. So you'll have your final answer as the pressure gradient P, and then you'll give something with respect to a partial derivative of x, and basically like this. Just right up here. Great, let's move on to the next question. All right, so for question 3 is asking for the gradient of phi. And right away, we're given phi. And as you can see, it's in polar coordinates. So right away, don't be scared. It's just the same thing, the gradient, but just in polar form. So let's first go over the definition of the gradient in polar form. So with phi, we're just using phi as an example. So we have same thing, the del operator, which is to denote a gradient as always. And we have phi right over here. And instead of x and y, we're using r and theta because that is in polar coordinates. Then same thing. We have the partial derivative of phi with respect to r. Then we have the unit vector for r. And then this is where it's a little different. We're going to also have 1 over r times the partial derivative of phi with respect to theta. This is always true. So please keep this in mind that you do have to multiply 1 over r to your final expression. So I know this is a bit trickier just because it's in polar. So let's just keep going. We do need to find this and this. So we need the partial derivative of phi with respect to r. And then we also need partial derivative of phi with respect to theta. And then again, multiply that by 1 over r, that second partial derivative right there. So let's just simply go over this one. So we have right over here, I'm going to just draw a line just to give us some space. Great, so we have our expression AR sine theta times 1 minus a squared over r squared. So we're first going to just take the partial derivative with respect to r. So a great way to approach this is to just expand the expression AR sine theta times 1 minus AR sine theta times a squared over r squared. And then if you cancel that r from the top and the r squared expression at the bottom, it actually simplifies to a sine theta a squared times 1 over r. And this 1 over r, don't get it confused. It's not from the above expression. It's just from canceling out ar sine theta times a squared over r squared. And that square gets canceled and that r gets canceled. That's how we're getting that 1 over r. It's not the same thing as over here with that 1 over r. Great. So if we keep going, getting that partial derivative. So let's set it equal correctly now. Taking the partial derivative with respect to r, we have a sine theta, because that r is canceled. Then we have right over here, we still have a sine theta a squared. That's all the same. Then as we know, taking the derivative of 1 over r is also the same thing as r negative 1, r to negative 1 power. So just using our power rule, we know the derivative of this is just simply r minus 1 times negative 1. So that's just negative r to the second power, negative second power. So let's bring this back right over here. So that's just r negative 2. And then this actually becomes positive. So let's just keep that in mind. The sign changes right there. Great. So when to keep going, we can simplify this even further. The partial derivative of phi with respect to r is going to be this expression. We can pull out that a sine theta. A sine theta, that means it's going to be 1 plus, then we have a squared over r squared. And this is just for the partial derivative with respect to r. When you do the same thing for in respect to theta, please make sure to multiply it by 1 over r as well before plugging it back in. Right over here, we do need to account for this 1 over r. Then, because the question is asking for the gradient at this point, which is also the same thing as asking for the gradient of p at x, y, it's not a specific point. So it's just asking for that general expression. So your answer should be just right up here, the same. Write it out down here actually, just so it's clear. Equals, you're going to have partial derivative phi with respect to r times the unit vector plus the partial derivative of phi with respect to theta. And please don't forget the times 1 over r times the unit vector of theta. That will be the answer that you are looking for. Great, let's move on to the next question. Okay, and this brings us to our final question, question number 4. And it gives us an expression for the velocity profile. And then now let's just go through this carefully. I know it's a lot of text, but if you just read through the question really carefully, you can see that you do have all the information you need. So let's try working through this together. So there are 2 parallel plates. What I like to do is when it's a question like this, I like to just draw it out. So let's just draw 2 parallel plates. That's 1, that's 2. There we go. Okay, so we have 2 parallel plates distanced by 2d apart along the y direction. So let's just remember this is the y direction. So that means we have this distance right here between these 2 plates is 2d. Great. Then we have a width. We're just going to put it right here. A width of W, and a length of L. So we have L right over here. Great. So this is what we are given. Then we have mu as the viscosity, and we have the negative partial derivative of P, and with respect to X as a constant pressure gradient drive for the flow, or which drives the flow. And then we have velocity as parallel to the plate. That's key right there. Velocity is parallel to the plate along the longitudinal direction, which is X, right over here. So this is X. So we have velocity, some velocity flowing down between two parallel plates this way. So we can see in the first question, it asks us to draw the velocity profile as a curve dependent of Y. So it depends on Y, and then we have actually negative D to D. So instead of just drawing, writing right here, we can erase the width and length for now. It's not too relevant. So we can see, I'm also going to erase this and this. So instead of writing 2D, we can actually write it as is. So we have right here, this is going to be D, Y equals D, and this is going to be Y equals negative D for a total of 2D, right? So this means that this right here, I'm just going to draw a dashed line. Doesn't mean that there's a dashed line in between these plates. It's just for us. We have Y equals 0, right? Great. So with this, we have to find the velocity profile. So an easy way to know this is we know two things. We first know the maximum velocity is always at the center of flow. Second thing is we also have our non-slip conditions or no slip conditions of the plates, where we know at these plates, velocity is 0. This is due to the no slip condition, right? So if we can arbitrarily draw this, I'm not going to solve it for you, but if you know that velocity, let's say we're just looking at this part right here, this is just an arbitrary line. And we know that velocity is actually going parallel to the plate in the longitudinal direction. So this way, we know velocity is like that. If we know the velocity is 0 here and 0 here, and we have the maximum velocity right over here as a vector, all we need to do is connect the dots. And of course, it's not going to be a straight disconnect right here. You're not going to have a disconnect. It's going to have to be continuous. So draw a continuous line that hits all of these points. I hope this makes sense. That means that maybe right around here in the Y, I guess this would be Y is D over 2. You would expect a velocity that's kind of in between, not 0, but also not max. So maybe like right around here, maybe a little bit further. Yeah, like that. And then you can kind of see what the shape is supposed to be. Going to just erase this to prevent confusion. Great, and then it also asks to write and draw the vector form of the velocity. Well, we already kind of did it right here, but what is the vector? Is the vector going in the Y direction? No, it's going in the X direction, and it's going as shown in this picture. Great, and we also, I do want to make a note. It's asking for the vector form of the velocity. Well, you are given the velocity profile. So we know that the velocity profile is dependent of Y. As you can see in this expression right here, there's no X values. So we know that velocity, just going in the X direction, is dependent of your position in the Y direction. let me clarify that one more time. The velocity in the x direction, right? This is x direction, is dependent of your position in the y direction. Great. So just write the vector form of the velocity and draw it. It's not rocket science, it's all on the screen. So I hope you guys can understand and figure it out. Great. Now let's move on to something we haven't talked about in the earlier questions. We have the shear rate. So the shear rate is found by taking the negative gradient. So let's just work it out. Negative gradient, the negative gradient of the velocity profile. What do we just say the velocity profile was? Velocity profile is right above, right here, and it's given Vx. So we have the gradient, the negative gradient of the velocity profile. Then that means, let's just take a look right over here. If we take the gradient of the velocity profile, we can see we have no terms in relation. We have to take the partial derivative of Vx with respect to x, but there's no x term, so that's definitely not there. We don't have z terms, so the only thing we have are y terms. So we take the partial derivative with respect to y for the gradient. So it's actually a lot simpler than we think. Don't be too scared about all these terms. It's just asking for the negative gradient. That's something that by now, if you're on question 4, we just spent the past 3 questions working on this. So I hope you can take this partial derivative. I will not actually work this out here in this question. So we have the partial derivative of Vx with respect to y. And with that, we also don't forget the negative. It says the negative gradient. Great. So what you need to do is just get that. And then lastly, it's asking for at y equals d. Y equals d. So make sure that ultimately after taking the gradient, you're finding it, you're plugging in d for y. And you should have, your answer should be the shear rate equals an expression. That should be your answer. Great. And now moving on to part 4 of question 4. It's asking us to find the flow rate. The flow rate, as we know, is signified by Q, the volumetric flow rate. And it asks you to find it by taking the integral of the velocity profile. So let's just start writing it out like this. So it's asking for the integration. You have your integral of the velocity profile, Vx, remember. Great. And then now ask across the surface area of the flow. So we know it's asking across the surface area. And we know the area, the surface area of the flow, we have right here are 2 plates. We have 2 plates, but if we kind of look at it in the 3D form, right, we have a y component, and we also have our width. And it's important to know that the width itself does not impact flow. What actually impacts flow? The y component. It's what we talked about right over here. The y component. The y component is what's important. So we know that area, the surface area is the y position and the width. So let's just erase this right over here. So we know that this, we know that it changes and actually impacts the flow. So let's just keep writing it. Q equals the integral of Vx times dy times W, because it's the y component that's changing. So as we know, width is just a constant. So we can carry this width outside of the integral, makes life a lot easier. Let's keep going. Q is equal to width times the integral of Vx and dy. Great. So now we need to take the integration of the velocity profile, and we have dy. What does that mean? It means for our bounds of our integration, we need to consider the y. And ultimately, we have it right here. It's negative d to d. So as you can see, you do actually have all the things you need in the question. It's more of kind of looking at things in a different perspective and trying out different things. In the end, you just need to keep doing practice to really solidify this knowledge. Taking this class, that's what's really personally helped me, getting used to just thinking about flow and just things in a different way. Great, so what you're going to do after this is just finish up the question. You're going to, now you have your integration bounds, going to go up here, plug this in right here, Vx. As you can see, there are a lot of things that are just constants. Boom, right there. Boom, you can take these out. You're only really going to be integrating this. So hopefully this has been helpful. I'm actually not going to finish this through. I think it would be a great challenge to just get your integral practice done. But ultimately, your answer should just be Q. And you shouldn't have any y terms because you are integrating over a specific interval. So you should be plugging in that d and negative d. And you should just have one expression right over here as your answer. So thank you all for joining and watching this video. If you have any questions about these questions or also 5 through 8, please come to my office hours on Tuesday, 5 to 6 p.m. on Zoom. Anyone from any section is welcome. I'd love to help you out. And for our quiz section on Monday, we'll be going over different questions and not this homework. So please be ready for that. But have a great rest of your night.